Now today we will see the design of important component of IC engine, that is design of push rod for walls. So this is the very important component present in the IC engine. So the push rod is designed as the column on the basis of buckling criteria. So the ratio of push rod is such that it fall in the category of long column. So let DO is the outer diameter of the push rod and DI is the inner diameter of the push rod. The ratio of DI to DO for push rod is always taken as between 0.6 to 0.8. So now here we consider the DI by DO ratio, that is nothing but outer diameter of push rod to inner diameter of push rod to outer diameter of push rod is equal to 0.8. The moment of inertia I of cross section is given by the formula I is equal to pi into the fourth ratio of DO minus DI. So that is the difference between DO raised to 4 minus DI raised to 4 divided by 64, and area is equal to pi into bracket DO square minus DI square by 4. So the radius of gyration is given by I is equal to AK square. So K square is equal to DO square plus DI square by 16. This is the standard formula. And we find K from Rankine's formula. So P is equal to sigma C into A divided by I plus alpha L by K square. Therefore, for a push rod made up of a mild steel and plain carbon steel, let L by DO is equal to 20 and sigma C is equal to 70 Newton per mm square. So this is the initial value for stress, compressive stress. The cost of steel rod is given by A is equal to 1 by 7,500. DI by DO ratio is 0.8. P is calculated by using this formula. So from this, putting all the values, given values, we'll get a L by DO ratio is equal to 20. After that, further solving, we'll get the DO square is equal to 80.368. Therefore, DO is equal to 16.7442 mm. So the round value of DO is 17 mm. As L by DO is 20, therefore length of the push rod is equal to 20 into DO. Therefore 17 into DO, you will get 340 mm as a length of the push rod. So the diameter of the push rod will be 17 mm and length of the push rod will be 340 mm. Now we can see the diagrammatic representation of that push rod here. So here force or pressure P is acting on the push rod. Then DO is the diameter of the push rod, which is equal to the 17 mm, and length of the push rod will be equal to 340 mm. This is the axis of the push rod. So in this way, we can design the push rod for wall based on the its diameter and length. Now today we will see how to design a crank pin. In the design of crank pin, two important parameters that we are going to see. One is the diameter of the crank pin, and second one is the length of the crank pin. So in a previous topic, we already designed a crank pin whose diameter is 55 mm and length is 55 mm. Since the diameter is more, the first case is the criteria is deciding the diameter of the crank pin. Therefore, DC and DL is equal. DC and LC is equal to 55 mm. Now we have to design the diameter or the shaft undergoes the flywheel. Therefore, the DS is the diameter of the shaft under the flywheel. So the center plane of shaft is subject to the maximum bending moment due to reaction R3. Therefore, MB is equal to R3 into C2. So it is also subjected to the torsional moment MT due to the tangential moment PT. Therefore, R3 is the R3 R dash 3 in vertical direction and R dash 3 in horizontal direction, square root of the square. Therefore, the R3 will be equal to 1180 Newton. The diameter of the shaft ds is calculated by the following equation. That is nothing but a ds cube is equal to 16 by pi into tau md square plus mt square in square root sum. Therefore, by putting the values, we will get the ds cube is equal to 116.30 into 10 raised to 3. Therefore, the diameter ds will be 48.812 mm. So, assume we are considering the round value ds is equal to nearly equal to the 50 mm for this shaft. Therefore, in calculation of the previous case, the diameter ds is 30 mm. Since the diameter is less, the second case is the criteria of designing the diameter of the shaft under the flywheel. Therefore, ds is the equal to 50 mm. Now, design of the shaft at the junction at a right hand crank wave. Therefore, let ds1 is the diameter of the shaft at the junction of the right hand crank wheel. Therefore, the ds of crank under the flywheel at the junction at the right hand, the crank will be subject to the following bending moments. So first will be the bending moment is vertical due to the force in vertical plane, that is R1R into PR into MBH, and due to forces in horizontal direction R1H and PT. Then torsional moment due to the tangential component is MBV and is calculated as 535.88 into 10 raised to 3 Newton mm. Then in horizontal direction, it will be the bending moment in horizontal direction is 314.27 into 10 raised to 3 Newton mm. Therefore, resultant bending moment is 621.24 into 10 raised to 3 Newton mm. So the bending moment resultant is calculated in the square root of the square of the bending moment in horizontal direction and in vertical direction. DMT is the bending moment is equal to the PT into R. Therefore, the MT equal to 897.939 into 10 raised to 3 Newton meter. Therefore, the diameter of the shaft ds1 is calculated by the following expression. ds1 cube is 16 by pi into tau, square root of the sum of the bending moment. Therefore, the ds cube will be 139.24 into 10 raised to 3. Therefore, ds1 is equal to the 52 mm. Therefore, the design of the right hand crank wave subjected to the following stresses. The bending stress in vertical and in horizontal plane. Then the direct compressive stress due to the radial component PR. and the torsional shear stress. That is, these are the three stresses are there. Therefore, the bending moment due to radial component is calculated by using this formula. After putting this formula, the bending moment due to the radial component will be equal to the 535.88 into 10 raised to 3 Newton meter. Also, MBR is equal to sigma b into r into bracket 1 upon 6 and w into t square. Therefore, sigma br is equal to 31.39 Newton per mm square. Therefore, the bending moment due to the tangential component at the junction of crank web and shaft is given by and is calculated as a 586.65 into 10 raised to 3 Newton meter. Also, it is calculated for the sigma b is equal to 21.4839. So in this way, the direct compressive stress due to the radial component is also given by sigma c for d is equal to PR upon 2 times W into T. So by putting the value, we will get the compressive stress 3.98 into 3.9872 Newton per mm square. Therefore, the maximum stress is given by sigma c is equal to sigma br plus sigma bt plus sigma c d. Therefore, sigma c is equal to 56.87 Newton per mm square. The torsional moment on the arm is given by mt is equal to r2h d2 minus l1 by 2. Therefore, the torsional moment is calculated as a 434.0042 into 10 raised to 3 Newton mm. Therefore, shear stress is calculated by the formula mt upon zp. So that will be equal to tau is equal to 19.07 Newton per mm square. The maximum compressive stress is calculated by this formula sigma c max is equal to 1 by 2 into bracket sigma c plus square root of sigma c square plus 4 times tau square. So the maximum compressive stress is calculated as 62.67 Newton per mm square. The above values of sigma C max is less than the allowable compressive stress, that is 75 Newton per mm square. Therefore, our design is safe. Next, design of left hand crank wave. The left hand crank wave is not severely stressed due to the extent of the right hand crank wave. Therefore, it is not necessary to crank wave the thickness and width of the left hand crank wave are made equal to that of the right hand crank wave from the bending consideration. Then design of the crank bearing. The bearing too is subjected to the maximum stress. The reaction at the bearing is calculated by the formula R2 into square root of these parameters. That is nothing but a reaction in vertical direction and a reaction in horizontal direction. Therefore, the R2 will be 12,785 Newton. The diameter of the journal at the bearing 2 is DS1. Therefore, DS1 is a 55, which is calculated. Then the L by D ratio for the bearing is given by PB is equal to R2 upon DS1 into L. Therefore, PB is equal to 4.22 Newton per mm square. So PB is less than 10 Newton per mm square. So the bearing pressure is within the limit. Hence, the design is the same. So in this way, we can design the various components of the crank shaft and crank pin.